So, have you ever looked at a really powerful AI and wondered, how did it get so smart? Well, it's definitely not magic. It's actually a series of incredibly clever engineering plays. And today, we're going to open up that playbook and show you two of the core strategies that turn good models into absolutely fantastic ones: data augmentation and transfer learning.
But let's start with a basic question. What do you think is the one secret ingredient every single powerful AI model has to have? Is it some genius-level algorithm? A mountain of super-fast GPUs? I mean, yeah, those things are important, for sure, but they aren't the main ingredient.
It all comes down to data. And I don't mean just a little bit of it. We are talking about massive, almost unimaginable amounts of data. This is, without a doubt, the single biggest challenge and the most valuable resource in AI today. But what if you don't have an ocean of data? Well, that's where the smart plays really begin.
So here's our game plan. First, we'll talk about AI's unbelievable appetite for data. Then we'll get into the art of data augmentation, basically how to make more data from what you've already got. After that, we'll see how we can learn from the giants using something called transfer learning. And finally, we'll wrap it all up in a step-by-step tuning playbook.
Okay, let's start with a fundamental problem. You see, deep learning models are just incredibly data hungry. To learn how to spot something like a tumor in a medical scan or a pedestrian on the street, they need to see thousands, sometimes millions of examples. This data bottleneck is the core challenge that pretty much every AI engineer has to face.
So how do you feed that hunger? The first play is called data augmentation, and the idea behind it is brilliant in its simplicity. You take the data you already have and you just create more of it. You generate new, synthetic examples by tweaking them in ways that, and this is the most important part, don't change what the data actually is.
And you know, it's not just some mechanical process. There's a real art to doing this right. It's a creative way of making more from less, of intelligently expanding your data set without having to go out and collect a single new piece of real-world information. This is where engineers get really clever to make their models that much smarter.
So, why even bother with all this? Well, obviously, you make your data set bigger. But what's more important is you teach your model to generalize. It learns to focus on the things that actually matter, like the shape of a stop sign, not the specific lighting or the exact angle it's viewed from. This is what makes an AI in, say, a self-driving car robust enough for the messy, unpredictable real world.
But there is one golden rule here. You have to preserve the meaning. And this example just perfectly illustrates the point. If you take a picture of a cat and you flip it horizontally, guess what? It's still a cat. No problem. But if you take an image of the number 6 and you rotate it 180 degrees, well, now it's a 9. You've just changed the label and you've totally confused your model. So the key takeaway is the transformation cannot change the answer.
Now, there are a bunch of ways to augment data, and they usually fall into a few main categories. You've got your basic geometric tweaks like flipping and rotating. Then there are photometric changes, where you play with things like brightness, contrast, and color. Then we get to the more advanced stuff, like region-level augmentations, and even fully automated systems that learn the best way to augment the data all by themselves.
Let's look at a pretty cool example of a geometric transformation. This is called elastic deformation. See how the grid on that original brain scan is kind of stretched and warped in the second image? This simulates the natural variations in shape you'd see in the real world, and it's incredibly useful in fields like medical imaging. It helps models recognize anatomy, even with slight differences between patients.
Now check this out. This is a technique called cutout. You literally just cut a random square out of the image. You might be thinking, why on earth would I do that? Well, it forces the model to learn from the entire object. It can't get lazy and just focus on, say, the cat's ear to identify it as a cat, because hey, next time, that ear might be missing. It has to learn from the tail, the body, the whiskers, everything.
Okay, this one is really clever. It's called mix-up. You take an image of a cat and an image of a dog, and you literally blend them together along with their labels. What you get is this weird ghost-like cat-dog hybrid. Now, it sounds completely crazy, I know, but it's a surprisingly effective way to stop the model from becoming too confident in its predictions, and it really helps it generalize to new things it hasn't seen before.
So instead of picking all these transformations by hand, we can actually automate the whole process. This table kind of shows the trade-offs. You've got auto-augment, which uses really complex reinforcement learning to find the absolute best policy, but it's super expensive to run. On the other end of the spectrum, you have trivial augment, which is incredibly simple and cheap. And right there in the middle is rand augment, which is a fantastic sweet spot, giving you great results without that massive computational cost.
So augmentation is great. It helps us multiply our data. But what if we could avoid starting from scratch in the first place?
Well, this brings us to our second major strategy, transfer learning. This isn't just about making more data, it's about making the entire training process way more efficient by, well, standing on the shoulders of giants. Here's the core idea. You reuse the knowledge from a model that has already been trained by a big lab on a massive dataset. Think something like ImageNet with its millions of images. We take that pre-trained brain and we adapt it to our new, very specific problem. Basically, we're not reinventing the wheel, we're just putting some new tires on it.
And the benefits here are just incredible. Your model trains way faster. It generalizes better because it already has a basic understanding of what things in the world look like. For a startup or maybe a small research team, this isn't just a nice-to-have. It is the essential strategy that lets them compete and build powerful AI without needing a Google-sized budget.
So let's look at how this actually works. Imagine a big model that's been trained on 1,000 different categories. Its early layers have learned to see universal features, things like edges, colors, and textures. With transfer learning, we keep those foundational layers and we freeze their knowledge. We basically just chop off the final layers, the part that was making the 1,000-category decision, and we stick on a new, smaller head that's custom-built for our specific problem. This means we only need to train that small new part, which saves a massive amount of time and data.
Now, there are two main ways to do this. The first is called feature extraction, which is exactly what we just described. You freeze the base and you just train the new head. This is perfect when you have a pretty small data set. The second approach is called fine-tuning. For this, you actually unfreeze some of the later base layers and you train them just a tiny bit, letting them adapt to your specific data. This works best when you have a bit more data to work with. Okay, so we've got our two powerful plays for handling data. Now, let's put it all together into a practical game plan. This is the tuning playbook, a systematic process for going from just an idea to a highly refined, powerful model. And the very first play in this book is by far the most important one. You've all heard this quote before, garbage in, garbage out. It is the absolute #1 truth in machine learning. None of these advanced techniques we've talked about will save you if your initial data isn't clean and reliable.
So here are the 6 steps. 1. Start with quality data. 2. Build a super simple, naive baseline model just to make sure your pipeline is working. 3. This is a key debugging step. Try to make your model perfectly memorize a tiny little batch of data. If it can't, something is broken. 4. Once that works, you gradually scale up. 5. If you start to overfit, which means the model is just memorizing your data instead of learning from it, that's when you bring in regularization plays, like the data augmentation we just discussed. And 6, you just iterate, slowly increasing complexity and adding regularization as you need it.
And this flowchart here, it visualizes that entire process perfectly. It's not a straight line. It is an iterative loop. You build something, you test it, you check for bugs, you scale up, you check for overfitting, you regularize, and then you do it all over again. This systematic workflow is really what separates the amateur attempts from the professional, state-of-the-art results.
So, we've covered the smart plays, creating more data when you don't have enough and borrowing knowledge when you can't start from square one. These aren't just little tricks, they are the fundamental strategies that really make modern AI possible for everyone. So, now that you have the playbook, what's the first problem you'd want to teach an AI to solve?